welcome in. So this is a little quiz on the nuclear energy chapter. I will put this exact quiz so that you can download it in the description. I'll put all the kind of references as well so that you can take a look and peek at those. And I'm gonna just take up this entire quiz. It has 5 questions. Now, some of them have multiple items. I'll try to also timestamp it so you can go to any question that you like. All right, so let's dive in. So here's the first question that I have for you, which is, how is a radioisotope related to nuclear energy? Now, there's a table in here of the various kind of nuclear reactions that can take place. I want to tie this into this question. So first of all, radioisotope. So the word, my assumption is that you do understand what an isotope is. Now, once you understand what an isotope is, if you want a little bit more in terms of details on these, I'll put up a link up above there to the introduction. But the key word here is radio. Now, the radio is tied into radiation. Now, we don't use radia, but you can see right here. So that is the tie-in to the actual radiation itself. So how are these two related? Well, first of all, a radioisotope is basically an unstable isotope. And for that matter, because it is unstable, it is in a state where it does not like to be. So it will try as best as it possibly can, okay, because of that instability, to either release, energy in some particular way. Now, that release of the energy can happen in kind of different ways. Well, it can happen through either a release or a capture of particles. So that's what can happen there. And these release or capture of particles can be seen as you go over nuclear radiations. Again, if you want a little bit more detail on these, I'm going to put up a link up above there. Now, as you can see here, so the release can be possibly kind of alpha decay, where you have an actual helium, which is released. You can have beta decay. Now, there's actually 3 betas in here. So one which is negative, positive, and electron capture. So it can release within here. So notice, right there. So what it releases in there is an electron. It releases here a positron right here, or it captures an electron right here. So all of these are the actual particles that can be emitted, or taken in for that unstable isotope. And that is the instability is the radio component, because radio is coming in because of the radiation that it gives off. And radiation is captured in this way, that it can be either particles or it can be releasing electromagnetic waves. Electromagnetic waves. That's what it can release. Now, this you can think of as some form of energy, that might be released. And hence, this is called the nuclear radiation. Now, nuclear, because it happens within the nucleus of that atom, so that's why it's nuclear. And the radiation is the giving off, possibly either of particles or electromagnetic waves, or just simply you can think about in terms of energy. Now, one of those examples of these electromagnetic waves can be this gamma ray that is released in there. So that is the gamma decay. That can happen right there. And as you can see there, so it goes in, so it's excited nucleus, it is at an excited state, and it wants to get back into a lower energy state, and it gives off that particular gamma ray photon, which is just the electromagnetic wave. So that is the tie-in between the two. All right, so the radioisotopes and the nuclear radiation that it can possibly give off. Okay, so that's question number 1. Check. Let's take a look and dive in here to question number 2. Here is question number 2. Now for this question, I'm going to take a look and right here and utilize this table. So back and forth so that you can easily see the alpha decays, beta decays, etc. So for all of these. Now let's break them down one by one. So I'm going to take a look at first A. So in this question, so this is an alpha decay of uranium-238. Now, if you look at alpha decay in general, so what happens in alpha decays is that you have an actual emission of an alpha particle from the nucleus itself. So that's what happens in general for any alpha decay. Now, this is a very specific one, so we're going to capture this one. So notice that you have a parent right here. So this parent for us is the uranium, okay, that we have. And that particular uranium, so it's 238. So this is 238, which is the atomic mass. And now for uranium, we can kind of go back in here into our periodic table and find uranium in general. So you can kind of zoom in there. So I'm going to just zoom in right there. So uranium has mass, okay, of 92. So this is the atomic number, okay, in terms of that. The mass is 238. So this is 92. And now from here, so what it gives off, so this is the process of shooting out, and this is going to now be the daughter, which is the changeover. And notice that what I like to always do is I know that there is a helium which is always released in the alpha. The helium is always of size 4 on its atomic mass, and it has 2 protons, which is its actual, okay, within its nucleus. So within this, notice that this will lose 2 of these right there, and it will also lose 2 neutrons as well. So therefore, so if it breaks down, it's going to bring this back down, and it's going to have 234, okay, as its mass. And the atomic number is going to drop down by 2. So this is 90. Now within here, so you can now go back. Okay, so if it drops down to 90, so notice that that is thorium, which is going to be TH in here. I'm going to go back in here. So as you put in, so this you can now label TH. And here is your alpha decay for this part A. Now for part B, so if I'm going to jump into part B, so I'm going to try. So within here, in part B, we are now dealing with a beta negative decay. So this is for carbon. Now in general, so for beta negative decays, right there, so what we have is the following. That a neutron, okay, changes into a proton, and it is emitting an electron in general. All right, so this is what's going to happen in here. So I'm going to paste this right there. I'm going to have to kind of delete this shortly. So in this situation, so as you can see here, so I am dealing with carbon. So my first, so again, so my parent, so this is going to be carbon. So this is 14 in here. Now carbon, so again, so in terms of trying to reach back in there, so if you forget, so carbon has an atomic number of 6. Okay, so this is going to be 6 right there. And now we can change this back in. So what happens? Well, an electron is given off. So here is an electron which is emitted, and the neutron changes into a proton. Now, if it changes into a proton, so as this electron is given off, so that means that all of a sudden, so the number of protons is going to increase, which is going to be now 7. Your atomic number does not change at all. So this just stays as 14 right there. And now, so if you're jumping into 7, so that's going to be nitrogen. So again, you can look back in here into your periodic table. So that's going to be your nitrogen in general. And this is now your beta. So in this case, this would have been beta negative decay, and the negative comes because of this electron. So that is the beta negative decay that we have. So that's part B. So now we have 2 of these, which we have within here. I'm going to just add a page just so that I have some space. Let me go back, and now we want to jump in, and I'm going to borrow this one out of here. So this is going to be for C. Okay, so right there. Now that's fluorine. So within here, so if I'm going to scroll back down, so paste it, and this is, they're asking us for beta positive decay. All right, so what does beta positive decay do? Well, beta positive decay, so right here, so this means that a proton changes into a neutron, and it actually gives off not an electron, but a positron within here. So if I scroll down, so this is the general case for any beta positive decay that happens. So now notice that your proton, okay, changes into a neutron. Okay, so proton changes into a neutron, which means that you're going to have one less proton in here. So my parent that I have, which is fluorine 18, so that is within there. So you can see, okay, so fluorine has 9, that's its atomic number in there. So I'm going to just go back in here. So this is going to be 18. So F and 18, and this is 9. Now it's going to change back in within here. So it gives off, this is why it's beta positive. So that's the positron, which is given off right there. And now it's going to have a decrease of the number of protons. So its atomic number reduces, but the atomic mass stays the same. So now if you go back in here, so notice if you zoom in here, so that is going to now change into oxygen. So that is what you're going to have right there. So that's oxygen right in here. So that's beta positive decay. And that is it for this. All right. Now let's take a look. So that's for part C. For part D, which is going to be this one right here. This is chlorine. So let's capture that within here. So let me paste it in. So that's chlorine right there. And now this is an electron capture. So what was electron capture? Well, an electron capture means that we're going to be capturing in an extra electron within. So it actually brings in an electron so that you have, so your parent right there. So notice that it captures in, so it captures of an electron by the nucleus itself and converting a proton into a neutron. And this is exactly what you see in here. So if it captures in, so that electrons get captured, so notice that your Z, okay, or your Z is now going to be one less because the proton, okay, is going to get converted back into a neutron. So that's what you have. And in order to write this down, so now chlorine, so 37, okay, so that's for chlorine in there. To take a look at chlorine, so right there, which is 17, right? So that's what it has on its atomic number. So I'm going to just go back in here. So that's within chlorine. Let's write this out. So this is going to be C, okay, L. So 17, and this is 37. And now plus the extra electron that it captures in. So this is going to get sucked in right in there, which means that all of a sudden you have a reduction. So instead of 17, it's going to be now 16 protons. The atomic number will stay the same, so that's 37. And now the only byproduct, so for 16, so we're kind of back in here, so notice that it's going to be sulfur, which is S. So that is what we would have to find out in here. And as long as you're using your periodic table, assuming that your teachers do let you use these, if you have to memorize all of these, it's going to be a little bit tough. I certainly don't memorize them anymore, just some few ones that are used very commonly, but the rest I just kind of look them up. So that would have been an electron capture right there. All right, so now the last component in here, which says, does a gamma decay cause a new daughter element? Well, so for this one, actually, I don't need to write this out. Does it? No, it does not. So if I go back in here, so this is the gamma decay. I'm going to blow it up. This is what you see right here. So your gamma decay, so this basically is kind of, as I said, in an unstable state, right? So this is one of the radioisotopes, this little star means that it's kind of unstable and it doesn't like it. Now, because it doesn't like it, okay, it actually gives off, okay, some energy. So it is in an excited nucleus, okay, to a lower nuclear state, but it is emitting a gamma ray photon. So that's how we designate this, okay, in terms of its reaction. But the parent and the daughter, so these two, they stay the same. It's still exactly the same atom that we are talking about. It's just energy that is given off so that it can come back to a lower energy state. So there you have it. So that is example number 2. So a really good one. It forces you back into alpha, beta, electron captures, gamma decay, and forces you to review these concepts and how to set up the nuclear reactions. If you want more nuclear reactions, okay, I put it up above there. So I did a video on this concept as well, giving some examples there. Here's the next example, so number 3. So it says that we have an unknown radioisotope and it is undergoing a beta negative decay. So that means an electron is given off, okay, in some way. All right, so it has parts A and parts B. So let's tackle part A first and let's see what they're asking us. Now, we don't know what this is, not that it matters. So within here it says, what is the half-life time? So we want to know what the half-life time is of a isotope. Okay, this would be, I guess, a radioisotope that starts off with 350 milligrams and it decays to 45 milligrams in 3 weeks. Provide your answer in days and then round it to 3 significant figures. Okay, so let's give it a try. So what are we given? Well, we want to be able to find out what the half-life time is. So that's what we want. Now we want this to be in days. We are given the initial starting point of the mass, which would have been 350 milligrams. We are told that this decays, so to a final mass of 45 milligrams, and this happens in 3 weeks. So this is the total time. So this is in 3 weeks. Now 3 weeks, so there's 7 days in a week. So we have 21 days. Now I'm going to change it to days because that's exactly what they want, right? So they're asking us to keep this in days. So if you go back to this, this is just a standard equation for half-life. So you can set it up in various ways. So one of the ways that you can set this up is that your final mass is equal to your initial mass multiplied by, so this is going to be the half-life, right? So this is decaying at 50%, so that's half-life, to, okay, the number of periods, so in this case, the number of days that pass by, right? So how many, okay, actually are going by for us. Now, n, which is the number of periods, is equal to the total time divided by the half-life time, right? So that's what n is. Now we can substitute that directly right into it, okay? Or we can just leave it as n and then solve for our half-life as needed. So I'm going to take this on the side here and I'm going to point out to you that if you do want the half-life, then this is just simply half-life is equal to the total time divided by the number of half-life periods that have passed by. So this is over n. I'm just rearranging this formula. So if I take now all of this, I'm going to substitute everything that's given. Well, my final, which was 45 milligrams, so check. Notice the units are identical, so I can keep them. My initial was 350. This is going to be 1/2 of n. So I'm going to just now solve for n. So what that is going to be, so 45 divided by 350 is equal to 1/2 n. And if you do this, then this is just n is equal to, and I'm going to now take this, you can use log or ln. So log of, this is 45 over 350 divided by the actual log of the base, which is 1/2. All right, so this is what I have in there. So this would give me what my n is. So let's pop out our calculator in here and let's take a look. So this is going to be log of, so this is 45 divided by 350, and then the whole thing divided by log, and this is log of a half equals, so that's n is equal to 2.959, I'm not going to write this out. Now, please remember, this is the total number of periods, so half-life periods that have passed by, so it's almost 3. Now, I can take this and substitute it back into here, right? So now I know t, so t was 21, so 21 divided by the n, and that's going to give us what the half-life period time is in days. Okay, so let's do that. So there you have it. So now, I just substituted it back in, and we get, so 7, and notice this, it says to round this to 3 significant figures, so I guess it's going to be 1 over, so it's going to be about 7.10, and this is going to be the number of days that it takes for one half-life. Now, what does that mean? That means that to go from, so we started with 350 milligrams. So if you want half of that, which would have been 175 milligrams, it would have taken about 7.1 days. And then again, if you want to half that, it's going to take another 7.1 days. Okay, and so on. And now we have gone through, so almost 3 iterations, okay, of this. So almost. All right, so that is going to tell us that it's, the number of days, okay, that we have in total. Okay, so within here, so that was part A. Now let's take a look and jump into part B. What percentage of the radioisotope would remain after 30 days? Okay, so after 30 days, what would remain? Provide answer as a percent rounded to 3 significant figures. Okay, so this is for part B. Now I'm going to add an extra page in here for myself just so that I have space. So for this, if you're doing this question, so we have already found out what the half-life is right there. I hope I kept it in there. I did. Okay, so I'm not going to delete it. So for that, it wants us 30 days later. So what percentage remains? So whenever you're working with percentages, this is always worth noting. So the initial, so this is going to be times 1/2. Now, this is going to be t. I'm going to put t over t 1/2. So this is really nothing else but n. But they're giving me 30 days, right? So I can find out exactly what n is. So n is going to be, 30 divided by the number that we've just found. However, because they want percentage, so what I recommend is instead of starting with anything that they give you, just start with 100, right? So 100 milligrams, for example, or 100 grams. And therefore, when you find MF, so as you substitute all of this in, so this is going to be 1/2, so T is 30 divided by, approximately 7.10 in here, that's going to give you a number, and that number is going to be comparison to the 100 right here. 100 meaning 100% you started with, and then how much do you remain with? All right, so let's punch all of this into the calculator and let's see what we get. So here's the answer, and so if you wanted to, in terms of percent, so this is going to be rounded. You can see there on the calculator to 3 significant figures. So you started with about 100 and now you're left with only 5.34%. So that would have been your answer. And notice that that comes out, okay, so the number of periods is actually quite a bit. Okay, so it's a little bit over 4. So you're just halving it, right? So this is what you would see. So the 100, okay, divided by 2, which would have been the first half, divided by 2 again. This is the second time. Divided by 2 again, this is the third time, and then divided by 2 again, which is 6.25. Now it still has a 0.227, etc., and that brings you down, into the 5 range. So there you have it. That's how you would have taken care of this example. That's number 3. Here's example 4, okay, or question 4 on this quiz. What is the mass defect and the binding energy for helium-4 that has an atomic mass of 4.002603 atomic mass units? All right, so we want to provide the answer in atomic mass units, also in kilograms. That's for the mass. and we want to find out what the energy is in joules and in mega electron volts. All right, so let's take a look. So it's asking us about two things, mass defect and binding energy. Now, these two are tied in together by the famous equation, energy is equal to mc squared. Now, this m is going to be the actual difference of energy in terms of the defect. So let's take a look how we're going to solve this particular example. So we have, so this is helium-4. Now, within helium-4, so we have, therefore, 2 neutrons, and we also will have 2 protons, right? So this is what we're going to have. Now, in order to find the mass defect, we already are told what the actual atomic mass is of this item. Now, the binding energy is the energy which is binding the actual nucleus together. So if you had these individual particles, so the neutrons were separated and protons were separated, okay, what we find is that there's a mass difference between the actual atomic mass and when you take them separately individually. And then when you bring all of those together and you create the nucleus, right, so some of that mass is changed into the binding energy within it. And that's what we want to be able to find. So in order to do this, I have to now find out within here. So these two, so this is going to be 2 times. Now, they actually give us, so the neutron right here, so they give us what the mass is, which is 1.00, this is 8665. Now, the protons, I have 2 of those, so I'm going to multiply this. They also give us that, which is right here, so that's the proton, times 1.007, 276. Now, combining these two together, so if I bring these two together and add them up, I'm going to get what the mass is, the individual components of that. Okay, so let's find out what this is. So there we have it. All right, so that is what the mass right there is provided. Now, notice that the atomic mass, so this, I'm going to just copy this, okay, and paste it back in here. I'm going to make it a little bit different. So that is the atomic mass of the helium-4 when it's all put together. Now, as you can see here, they're different, right? So this one is actually less than this. It's not by a lot, but it is less. And that is the mass defect. So the mass defect is really the difference between the two. So here is, okay, the mass that we have, that's on the individual side, minus the mass when they're all bounded together. So that's 2603. And this becomes 0.0, so 29279 atomic mass units. This is the difference. Now, where did that difference go? That difference has gone into the energy that's holding this thing together. And that's the equivalence between mass and energy that we have. So if you wanted to find out this, because it asks us to also compute this in kilograms. Now they tell us that 1 atomic mass unit is provided there. So I'm going to take this whole thing and I'm going to multiply it in. So it's going to be 1.66054 times 10 to the negative 27. All right, so it's super tiny right there. So that is 4.86, 1895, okay, etc. times 10 to the minus 29. You can certainly round this to 3 sig figs, which would have been 4.86. But I'm going to keep it because I need it so that I can calculate the actual binding energy. So this mass defect is bound in the energy. Now that binding energy, so this is the binding energy, is equivalent to the mass defect and then multiplied by the speed of light squared. This comes from Einstein's equation within here. So I have the mass defect right there. That's already provided to me. And I'm going to multiply it here by the speed of light. Now the speed of light, they are telling us, okay, so that's right here. It's 3 times 10 to the 8, so it's rounded. That's okay. So 3 times 10 to the 8, but I have to square this, of course. So I'm going to square this up, and it equals. And so it's not a very huge amount. It's very tiny. So 4.3757, etc. times 10 to the minus 12 joules. Again, so this rounded to 3 sig figs would have had a mantissa of 4.38. So that's fine. That's what we have right there. So great. Now, if you want this in mega electron volts, so mega electron volts, we would have to convert this. So this is in joules. Okay, so now here is the conversion right there. So you're going to be dividing this through. So answer divided by 1.6022 times 10 to the negative 13. So negative 13 equals, and that gives you, so 27, write it in there, 0.3. Now this one I will round to 3 sig figs. Okay, so there you have it. And that now provides you everything that they've asked for. So we have our mass, so here it is in atomic mass units. Here it is in kilograms. We have our binding energy, here it is in joules. And here it is in mega electron volts. So that's what you would have in here. And that completes this example. Here's the last example for this little mini quiz. So we have, in this case, nuclear fission reaction. So we want to be able to find what the energy released in this process would be, right? So what would be the energy released? So if you're looking at this entire thing, so there is one item which is missing in there. So this whole item is going to indeed have the energy that is going to get released in this process. So this is fission. So notice we have the neutron coming in. Okay, that neutron, this is plutonium, which gets shattered, and that shattered, okay, it's going to have barium right here. And it's going to get broken down into strontium as well. So this is what we have. And in that process between the BA, the SR, we also have 2 neutrons, okay, that are fired off. And now let's see if there's any energy, okay, in this nuclear fission that would also be given off. And this is typically utilized in kind of nuclear reactors. Now we don't technically use plutonium as much. We typically use uranium, which is 235. At least in kind of the CANDU reactors. You can look those up if you like. But let's take a look and see how, okay, this can be calculated. So in order to do this, you're basically taking in, so this is, you want to know what the mass of your products are, and then, mass of your reactants, my apologies, and then mass of your products. So you want to be able to know what the masses of those two are. So we're going to do that. I'm going to separate them into 2. Okay, so let's take this, copy, let's paste it in. So those are going to be my reactants. I want to know what the mass is here. So let's do that first. Now, in all of this, well, they give us these. So this is going to be, so 239.052156. This is atomic mass units. Plus, now there's 1 neutron in here. Now, a neutron, I'm actually going to borrow from the previous example in here. So I'm going to steal this away. So here's my, right there. That's the copy of the neutron that I have. I don't need really the proton in there. So I'm going to paste this in. Okay, so that's a nice cheat, okay, right there. And now I can add these together, right? So I'm going to get a certain amount right there, okay, within this range. Now, those are my reactants. Now, on the other side, so I'm going to now steal these, okay, copy, and then paste it. So I have this right there. And what will this give me? Maybe I'll switch color. So now I am interested in, all right, so now I have my barium. So again, so I'm going to kind of go back in here and borrow these out of here. So this is going to be 143.912006 plus, okay, now my strontium, which is 93.915361. And now I have 2 of my neutrons. So 2 times, and again, I'm going to duplicate this back in here, and that's what I would have. And this is going to give me a total sum. So I have my reactants, and then I have my products. So I'm going to just do the calculation, and let's see what that is. All right, so we're back. So notice that your reactants, it's more than your products. So there is a mass difference or a mass defect within here. So obviously, so that mass defect, so that what you have, due to the law of conservation of mass and energy, then what this tells us is that the difference in mass must have been in terms of, or changed into energy in general. So that difference that we will have, now this is in atomic mass units, so we're going to have to try to change it back into kilograms. Then we're going to utilize our equation. So this is going to be, again, the mass defect multiplied by the speed of light squared. And we're going to be able to find out exactly what that energy is. All right, so within here, so it says provide answer in mega electron volts. All right, so we'll do that. And we're going to take all of these calculations in. So first I'm going to do the mass difference within. So I'm going to calculate that. Then I'm going to change that into kilograms. Then I'm going to multiply it by the speed squared. And that's going to give me energy in joules. Now to change it into mega electron volts, okay, I'm going to have to do that conversion. All right, so let me do that and I'll be right back. And we're back. All right, so there you have it. Okay, so those are the calculations. So here's the difference, which is just a subtraction. Here's the changeover. So now, you have to have, okay, so within here, so that is the difference in between, so between atomic mass units and kilograms. So I used it from the previous example. Once you have that, you're going to be jumping in and multiplying it by c squared. So that's again from the previous example, which is 3 times 10 to the 8. And you get your answer in joules. And then now from joules, you just have to convert it back into mega electron volts, and I've rounded to 3 significant figures. Now that mega electron volts again is taken in from the previous example. So here's the conversion. I would not expect students to actually memorize all of these. This would be probably on a formula sheet or given to you like it is right in this quiz. All right, so that completes the entire quiz. I hope that you found this useful, and I hope that you've tried these on your own as well. All right, happy studying. Bye, everybody.